In this video, we will continue our discussion of time specifications. First, we're going to talk about the peak time. Um, and so the peak time is the time required for a system to reach um, its maximum deviation from the steady state value. So if I'm going to go ahead and draw an example of a step response. So we have a system that looks like this. Oh, we have a system. We have a system that looks like this. So some step response settling to some non-zero value. Peak time. So we look at the peak. This is the maximum deviation from the steady state value. And the peak time is the time it takes from time zero to get there. So T peak, and T peak is equal to pi over omega d. So it's basically half of a period. Um, we also have another time specification called the maximum or the percentage overshoot or the maximum overshoot. An overshoot is it's kind of intuitive. It's a measure of how far past the steady state value the system shoots before returning. Um, so it's a ratio of the maximum deviation um, to the steady state value. Um, and it's defined, we'll call it MP. So the maximum overshoot is by definition um, the absolute value of y of t peak. So that's the peak value minus y of steady state. And that's divided by y of steady state minus y 0. So it's a comparison of this value to this value. So that's y of steady state minus y 0. And this first one is y of t peak minus the y of steady state. We also have we can express this as a percentage. So this is the maximum percent overshoot is by definition equal to 100 times MP. So we take that ratio, we multiply it by 100, and that is the percent overshoot, the maximum percentage overshoot. So the maximum percentage overshoot, or the maximum overshoot is related to the decay ratio. It's the square root of the decay ratio, which we discussed in the previous video. It's also equal to, it's related to zeta e to the minus zeta times pi over the square root of 1 minus zeta squared. And And because it's related to the decay ratio, it's also directly related to zeta. So if you measure the maximum overshoot, you can directly get zeta with this expression, which is kind of a mess, but we'll go ahead and write it out. It's natural log of maximum overshoot, and that natural log is squared over the natural log of the percent overshoot. Square that whole thing plus pi squared, and all of this is underneath this big square root. The next quantity that we'll be discussing is the settling time and also the settling ratio. So the settling time is the amount of time required um, for the system to settle to uh, basically close enough to the steady state value. And that close enough is defined by the settling ratio. Time required for the response to settle within a specified amount. And that specified amount is the settling ratio. And so common values of the settling ratio, it could be 1%, could be 2%, 5 or 10%, these kind of round even numbers. Depends on your application. But really, what you're interested in is how long before the system functionally stops moving. Um, so if we'll draw another first order or second order step response here, um, the settling time is going to be um, the time it takes for the system to fall within and stay within a certain percentage of the steady state, so about 2%. So it's going to be somewhere around here, probably. Um, and then that time that you measure is the entire time right there. So this is T settle. Um, and so the settling ratio is going to be, and uh, to go ahead and state it more rigorously, um, settling time is the minimum value of t such that for all t greater than or equal to t settle, um, y of t minus y steady state, absolute value of that, divided by y of steady state minus y max is less than or equal to the settling ratio. So there's a few equations. So for zeta less than 0.7, um, settling time shows up as omega n times t settle is going to approximately equal minus the natural log of the settling ratio divided by zeta. If zeta equals 1, um, then you have 1 plus omega n t settle e to the minus omega n t settle equals the settling ratio. So these equations are getting pretty complicated. They get more complicated, but we'll just provide these. And for zeta greater than 1, so you can see this settling time applies also for critically damped and overdamped systems. Omega n times t settle is approximately equal to minus natural log of 2 times the settling ratio, I'll go ahead and abbreviate that, times sz over s2, we'll go ahead and define these in a second, over s1, where sz is a quantity equal to the square root of zeta squared minus 1. S1 is equal to zeta minus sz, and S2 is equal to zeta plus sz. So as you can see, analytically calculating the settling time can be difficult, but the settling time is one of the best ways to describe how long a system takes to respond, and one of the more useful ways, particularly when you want a system to get somewhere. When you're trying to control a system, the settling time is one of the more useful ways to talk about how well your controller is behaving.